Hello, myself Dr. Sudha from Government Science College, Autonomous, Bangalore. In this session, we shall see calculus of variations, in that properties of variation. We need some of the things which we studied in the previous session, that is definition of functional, variation of a function, and Leibniz rule for differentiation under integral sign, as well as partial differentiation of functions is a must for this session. Let us recapitulate what we studied in session 1. So we had seen variation of a function f, which was function of x, y and y dash, and it was given by delta f is equal to h into alpha into dou f by dou y plus h into alpha dash into dou f by dou y dash. So using this expression for variation of f, now let us see what is variation of y, which is equal to h into alpha dou y by dou y. So we are replacing f by y in equation 1. And we know that dou y by dou y is 1, whereas dou y by dou y dash is 0. So we get h into alpha into 1 plus h into alpha dash into 0, which gives us h into alpha. Similarly, we calculated delta y dash, and that was h into alpha dou y dash by dou y plus h into alpha dash into dou y dash by dou y dash. Here dou y dash by dou y dash gives us 1, whereas dou y dash by dou y is 0. So we get h into alpha into 0 plus h into alpha dash into 1. So we get h into alpha dash. Similarly, we find out the variation of f by substituting the values of h alpha and h alpha dash in expression 1. Now h alpha is variation of y, h alpha dash is variation of y dash. So substituting the values, we get the final expression for variation as delta f is equal to delta y into dou f by dou y plus delta y dash into dou f by dou y dash. And this was the expression which we derived for variation of a function f. Now let us see in this session the properties. So the properties of variation. The first property goes like this: delta of dy by dx is equal to d by dy of delta y, that is delta and d by dx commute. We need to show that these two commute each other, that is they satisfy commutative law. So let us prove this by taking the left hand side and showing that it is equal to the right hand side. So to begin with, left hand side is variation of dy by dx, that is delta of dy by dx. And now we know that this dy by dx is nothing but delta y dash. So we have found an expression which was marked as equation 3, and that gave us h into alpha dash. So substituting for delta y dash, we get h into alpha dash. Now h into alpha dash, what is this alpha dash? This is derivative of alpha with respect to x. So we can write h into d alpha by dx. Now h is a small parameter which was independent of x. Therefore we can bring this h within the derivation, that is d by dx of h into alpha. But what is h into alpha? Using equation 2, h into alpha was nothing but variation of y. So substitute h alpha is equal to delta y. Now this is nothing but the right hand side. So right hand side was d by dx of delta y, and we finally obtained the right hand side. Hence property 1 is proved. Now let us look into the second property. What does this second property say? If I is equal to integral x1 to x2 f of x comma y dash into dx, we know that this is a functional. Then variation of this functional, that is delta of integral x1 to x2 f of x comma y dash dx, is equal to integral x1 to x2 of variation of f. So that is nothing but this delta and the integral sign, they commute. So in this property, we need to show that the variation and the integration will commute with each other. In property 1, we proved that variation and derivation commute with each other. Now, similar to the property 1, here also we are going to check from left hand side to right hand side. So what is given? I is given, that is integral x1 to x2 f of x comma y dash dx. Let us call this expression as star. Now since this I depends on y and y dash, we have variation of I. So variation of f, that expression we are going to use for variation of I, and that is dou I by dou y into delta y plus dou I by dou y dash into delta y dash. Here we have used the expression for variation of f. Now let us use Leibniz rule for differentiation under the integral sign in this star. So here we require dou I by dou y as well as dou I by dou y dash. So I need to be differentiated with respect to y as well as y dash. So here you have the integral sign. So here we are going to use Leibniz rule for differentiation under the integral sign. So the first expression, that is dou I by dou y. So here this is I, we are going to differentiate that with respect to y using Leibniz rule of differentiation under the integral sign. You can write integral x1 to x2 dou by dou y of f dx into the variation of y delta y, plus the second expression integral x1 to x2 dou by dou y dash of f of x comma y dash dx into variation of y dash. This is obtained using Leibniz rule of differentiation under integral sign, and this is the expression for variation of I. Now let us simplify this. This is nothing but derivative of f with respect to y partially into the variation of y into dx. Similarly, in the second expression, this is the partial derivative of f with respect to y dash. So dou f by dou y dash into variation of y dash into dx. In both the integrals, the limits is same, that is x1 to x2 as well as we have with respect to x. Therefore, we can remove common factor and we can write integral x1 to x2 dou f by dou y into delta y plus dou f by dou y dash into delta y dash into dx. And the expression within this ordinary brackets is nothing but variation of f. So variation of f is nothing but delta f into dx. Therefore, we have proved that delta of I, that is I is nothing but the given functional integral x1 to x2 f of x comma y dash into dx, and that is equal to integral x1 to x2, and we obtained that to be variation of f, and variation of f can also be written as delta f of x comma y dash dx. Hence, we have proved the second property. Now let us move on to the third property. So the third property says that if u and v are functions of x comma y dash. So here we have two functions, both are functions of x, y and y dash. Then we need to prove that variation of C into U is equal to C into variation of U, where C is a constant, and variation of C is equal to 0. Third property says here, that is variation of A into U plus or minus B into V is equal to A into variation of U plus or minus B into variation of V. And the fourth one says that variation of U into V, this is product of two functions, is equal to U into variation of V plus V into variation of U. This is similar to the properties of differentiation. And variation of U by V. So here we are using similar to the quotient rule. So V into variation of U minus U into variation of V divided by the denominator square, that is V square, provided V is not equal to 0. Now in this third property we need to prove all these 5. So let us begin with the first one. So what is given? U and V are functions of x, y and y dash. So you can write U of x comma y dash and V of x comma y dash. So for any function f of x comma y dash, we have an expression for variation, that is delta f is equal to delta y into dou f by dou y plus delta y dash into dou f by dou y dash. So let us begin with the first one. Here we need variation of C into U, where C is a constant. So using this expression for variation of f, now you can write variation of Cu just by replacing f by C into U. So you get delta y into dou y of Cu plus delta y dash into dou y dash of C into U. Here we know that C is a constant, so it can be removed outside the differentiation, and we can write delta y into C into dou u by dou y plus delta y dash into C into dou u by dou y dash. Now in this expression, now you can remove C as common factor and you can write C into delta y into dou u by dou y plus delta y dash into dou u by dou y dash. And this expression, when compared with the variation of f is replaced by u, therefore it is variation of u. So we get C into variation of u, and that is the required result. Next, let us move on to the second one, that is, we need to prove that variation of a constant C is equal to 0. So here the function f is taken to be the constant C. Since it is a constant, its derivative, that is f with respect to y, becomes 0, f with respect to y dash also becomes 0. So now this implies that variation of C is equal to delta y into 0 plus delta y dash into 0. So 0 plus 0 gives us 0. Therefore, variation of C is equal to 0. Now let us move on to the third one. So here delta of AU plus or minus BV. So here we need to find variation of A into U plus or minus B into V. So using the variation expression, it gives us dou y of AU plus or minus BV into delta y plus dou of AU plus or minus BV by dou y dash into delta y dash. So now let us differentiate this AU plus or minus BV. We know that how to differentiate. We differentiate term by term. Therefore, we get dou by dou y of AU plus or minus dou by dou y of BV. Similarly, dou by dou y dash of AU plus or minus dou by dou y dash of BV. Now let us differentiate the first term here. So A is a constant, so retain A as it is and differentiate U. So you get A into dou u by dou y into variation of y. And similarly, here the u term, we get a into dou u by dou y dash into variation of y dash. So that is what here we have put here. So here we have dou u by dou y dash into delta y dash. Now collect the terms containing b. So here you have b into dou u by dou y. Here you have b into dou v by dou y dash. So you get b into dou v by dou y dash into delta y plus dou v by dou y dash into delta dash. So the expressions within the square brackets are nothing but this is variation of u, whereas this is variation of v. So now substituting that, you get a into delta u plus r minus b into delta v. Therefore, we have proved the third property. Now let us move on to the fourth one. The fourth one is variation of product of two functions, that is u into v. Let us once again use the variation expression. So you get delta y into dou y of uv plus delta y dash into dou y dash of u into v. We know how to differentiate product of two functions. So use the product rule of differentiation and you can write delta y into u into dou v by dou y plus v into dou u by dou y. That is first function into derivative of the second function plus second function into derivative of the first function. Similarly, plus delta y dash into u into dou v by dou y dash plus v into dou u by dou y dash. Now let us collect the terms containing u and v separately and you get u into dou v by dou y into delta y plus dou v by dou y dash into delta dash plus v into dou u by dou y into delta y plus dou u by dou y dash into delta dash. So the expressions within the square brackets is nothing but variation of v and here this is variation of u. Let us substitute that. You get u into delta v plus v into delta u and this is the required result. Now let us move on to the last property here, that is variation of quotient of two functions. So delta of u by v is equal to, let us once again use the variation expression here, delta y into dou y of u by v plus delta y dash into dou y dash of u by v. So that gives us delta y into, so here this is nothing but the differentiation of quotient u by v. So let us use the quotient rule of differentiation. So you get denominator into derivative of the numerator minus numerator into derivative of the denominator whole divided by denominator square, that is v square. And similarly the second term delta y dash into derivative of u by v with respect to y dash. So we get v into dou u by dou y dash minus u into dou v by dou y dash divided by v square. So here in both the expressions we have v square in the denominator, so you can remove 1 by v square throughout common and let us collect the terms containing v and u separately and we get 1 by v square v into dou u by dou y into delta y plus dou u by dou y dash, that is this term, into delta y dash minus both the u terms are negative, so minus u into dou v by dou y into delta y plus dou v by dou y dash into delta dash. But the terms within the square brackets are nothing but variation of u and variation of v. So we get 1 by v square into v into delta u minus u into delta v and here we need to give the condition v is not equal to 0, otherwise it is not defined. Hence we have proved the fifth property. So these are the three properties which we have in variation of functions. Now, at the end, let us define what is variational problem. So, variational problem can be stated as a problem to find a path y is equal to y of x in one dimension between x1 and x2 such that the line integral of f of x comma y dash, which is a function of the independent variable x, dependent variable y, and its derivative y dash, is an extremum. Or we can also state that as symbolically the problem is stated as for a function f of x comma y dash, the integral I of y is equal to integral x1 to x2 f of x comma y dash into dx along the path y is equal to y of x between x1 and x2 is to be an extremum. Hope everybody could follow all the properties and the statement of the variational problem. So let us end this session here and let us continue in the third session. Thank you.